In this review of this worksheet, we're going over some very important skills, some very basic thermodynamic skills that are centered on two things. On the tablature values that are given to you. Notice I have heats of formation given to you here, and then we have absolute entropies. And we can, of course, from absolute entropies, we can derive a change of entropy of my system, which is tied to the change of the molecular order or the degrees of freedom of atoms. And of course, this right here, the heat of formation, can give me the delta H of my reaction. And that tells me something about the energy going into or out of the system, because indirectly, this can give me the delta S of the surroundings, right? And from these values, okay, you should recognize that delta H of the reaction and delta S of the system can be used for this important formula of Gibbs free energy for total spontaneity, which is delta H minus T delta S. Of course, that's of the system, the tablature. So it's important that you realize that. So let's get down into and get started. All right, so the first part is from the data above, given the in this case, the oxidation of glucose. This could be cellular respiration. We want to know what the delta H of the reaction is. Okay, notice the little zero at standard conditions because we're using the tables at standard conditions. Now, this is our formula, and we've been talking about this at length, products minus reactants. It's a convention, and it's done that way so that we get the correct sign for increasing delta H for endothermic, or what, decreasing, that means energy is released for exothermic. Now, what I did for you is I took the what? The products, and I put them over here because so many people want to just go find the heats of formation of these guys as written, and they wind up doing what? Doing reactants minus products. So I kind of helped you along. So to do this, it's the sum of the heats of formation of the reactants. And in any case, we're going to do the products first. Let's be crazy and go in order. So the products are CO2, and I put them there. So 6 times the heat of formation of CO2, and we look at our tablature. CO2 has a heat of formation of negative 393, and we put that in. And so negative 393.5. And of course, we're going to add that because it's the summation, right, of 6 times, because the delta heats of formation per mole of H2O liquid. And you notice we're going from the tables given to us, because in a real AP problem you won't be given, pages of tablature. They'll put that right there into the problem. So H2O liquid is negative 285.83, negative 285.83. Okay, and that really worked out well for me. And so 285.83. And I'm going to put a bracket around here because this is the what? Sum of all the heats of formation of my products minus now the sum of my reactants. My reactants are glucose. I have that written here. So glucose liquid. And if I look on my handy dandy table above, I get negative 1271. And there's only one of them, so this is per mole, so we're good. And I'm summing, right? The sum of all the heats of formation reactions is 6 times CO2, 6 times oxygen, O2, and I don't have to look. You shouldn't have to look because you should know that's 0, right? Because it's an elemental state. And so when we put this in our calculator, 6 times negative 393.5 plus 6 times negative 285.83, take that entire result and minus it by negative 1271, what you get is a delta H of negative 2804. I'm not worried about sig figs here. 0.98 kilojoules per mole. Obviously, if we're going to round to sig figs, we'd go to the least significant number, and I'd probably go to, in this case, we would go to 3, even though that's a 0 there. Okay, and so no worries, kilojoules per mole. All right, and because this table is based on kilojoules. All right, now from the data, calculate the delta S for the combustion of glucose, which is the same reaction. And notice I was very nice. I put the products here, And the reactants here, obviously you're not going to have that, but delta S is done the same way. It's the sum of the products. So again, the products are going to be CO2, 6 of them, and 6 water molecules. It sounds very simple, but I want you to go through it. So we're going to go 6 times the what? The absolute entropy. That's the how much degrees of freedom do we currently have in our CO2, and that'd be 213. Notice all of these are positive. Absolute entropies are positive. They start from 0 at 0 Kelvin, third law of thermodynamics, and they increase as they get more complex or what? Become gases or so forth. So we've got for CO2, 213.6. Okay, so 6 times that because there's 6 there. All right, and so 6 times 213.6. And of course, it's plus 6 times of the water, another product. Okay, if we look at our table, water is what? Don't look at heat of formation. We're doing what? Absolute entropies, and it's 69.95. And it's, of course, 6 times that. And I put this in brackets because it's the sum of all of the absolute entropies of my products minus the sum of my reactants. So if I look at my reactant, which is a glucose, into my table, I see that glucose is 209 absolute, and there's only one of them, so it's just per 1 mole, 209. Okay, 0.2. All right, and there's only one there, and it's plus 0, right? Wrong. The what? Heat of formation is 0 because it's an elemental form, but not the what? Absolute entropy, because O2 is a gas. It has some degree of freedom, sure. So it has a value. In fact, it's pretty big when you think about it. So it's going to be 6 times. Look at the value here when you look at it. So for oxygen, it's 205. Whoa, compared to the others. Now why? Because it's a gas. Gases have tremendous degrees of freedom. So much so that they have almost no attractive forces, okay, within other gases. That's why they're called almost ideal. All right, and then we put that together. So when you do this arithmetic, okay, you get a positive 261.188 joule mole kelvins. And I want you to understand something. That's joule mole kelvins. And we at delta H, we have kilojoules. Now, why is there a huge difference? Because in our tablature, entropy changes are never going to be in terms of energy anywhere near the energy changes of energy released. Remember, the heat released is incredible for endo and exo, but the actual energy changes for degrees of freedom are never going to be as big. So that's why they use joules for entropy and kilojoules. It's an important distinction when we do the next part of this skill, which is now to calculate the delta G. And we're going to calculate delta G, okay, using this formula here. Okay, and again, these are all formulas given to you. Now, we could calculate delta G for this reaction, okay, if I had the Gibbs free energy of formation of the reactants and products. I can do the same exact formula if I had another column here that was delta G of formation, like the ones I've been showing in class. But they didn't give you that in this problem, so guess what? You can't do it. So the only way to calculate for delta G is you're going to have to use the what? The values that we got from the tablature that we just calculated for to plug in. So delta G is going to be equal to what? Delta H. Now the delta H, party people, that we just got was negative. All right, so it was going to put that negative 2804.98, and that's kilojoules, right, per mole. And it's minus the temperature. Okay, now this temperature always in Kelvin. It wouldn't make any sense to use a Celsius and negative. We want an absolute scale because that'll mess up our signs here. So that's going to be let's pick, well, it's at standard conditions. So standard conditions is 25 degrees Celsius. And to convert that to Kelvin, we add 273. And so what we get is 298 Kelvin, so 298. Okay, and we times that by the delta S of the system, which we got from tablature, all right, which is 261.1118. And if you put that in here, you're going to get a wrong answer because that's in joules. You have to be aware. This is a classic mistake in this AP problem where people want to put what? Joules in here when this unit is in kilojoules, the delta what? H. So what we do here, party people, remember this is a joule, this is 261.188 joule mole Kelvin. Okay, you're going to times it to get kilojoules. Well, we've been through this a lot through this course. To get rid of joules, joules go on the bottom. We want kilojoules, and what do we know? There's 1,000 joules per 1 kilojoule. So essentially, I'm dividing by 1,000. So this value becomes 0.261. Okay, and you can put the rest in if you like. Okay, 188, and that's now going to be kilojoules per mole. Okay, notice this is going to be Kelvin. And notice this is, if you remember, the unit is going to be what? Kilojoule per mole Kelvin. And that's what's written down here. So if you've got kilojoule per mole Kelvin, you notice what's going to happen is the Kelvin is going to cancel with this temperature. And then, of course, what we'll get is kilojoule per mole minus kilojoule per mole. And what we'll get is what? Kilojoule per mole. And so when we do the math to plug this in, all right, the delta G, when we do the math, negative 2804.98 minus, that's the delta what? H minus T, temperature in Kelvin, times the entropy of the system, you get a delta G that's negative 2882.8, and of course the unit is kilojoule per mole. Okay, so what does this tell me? That's a huge negative. So this is incredibly spontaneous, which means, party people, we have a chemical reaction that is increasing the delta S of the universe, because overall a negative delta G means that we're going from what? A high free energy value from our what? Reactants to a lower free energy. And if we're doing that, delta G is negative. And that's a spontaneous process as we go down. All right, exergonic if you want to go there, but that's what we do. Now, interesting enough, let's evaluate what the delta H was. The delta H was negative 2804.98 kilojoules per mole. Now, I'm doing this because I want to evaluate the heat released in this reaction with the actual free energy that's available to do work with. Remember, the negative delta G is called free energy because it's a spontaneous process. Okay, this drop in free energy is the free energy that we could, use. Now we can't use all of it, but you get the idea. So the available free energy to do something and drive a system, possibly couple, okay, or those kind of things, that notice it's greater than the actual heat released. What? We had a reaction, heat was released in the combustion, and not only are we making the surrounding gas molecules what? Go faster. That's what this part is. This part really, from the first video you watched this weekend with me, is the delta H. Really, this value is really what? This is the delta S of the surroundings. So it being so exothermic made the surroundings what? Entropy increase a lot. But, very important, how can we have more free energy than the heat released? Because this was positive, party people. Delta S is positive. That means in the system, we have an increase. In this box, there's a bit of an increase of degrees of freedom. So the entire universe is the surrounding and the system. So in the surrounding, delta S is increasing, and in this box, if you want to think of it as the reaction happened in a box, okay, the delta S of the system also increased. Delta S of the surrounding increased because we gave it heat to go faster and disperse. But in the what? Inside the system, we've got a positive delta S. Now why? Well, if you look at the reaction, we've got a liquid and 6 gas molecules. That's 7 molecules. And we produced how many? 12 gas molecules. Whoa! What happens there, party people? Well, we went from 7 molecules to 12. So we have more degrees of freedom just by more molecules. On top of that, we went from 1 liquid and 6 gases to 6 gases and 6 liquids. All right. So if you think about it, all right, the bottom line here is that there's a greater number of increase in individual molecules. The molecules got smaller and there's more of them, more degrees of freedom. And that's what made that delta G free energy larger, okay, than the heat released. So you're able to do what? More work. Okay, you had more free energy available than the actual heat released because of the what? Increase of entropy of the system molecules dispersing out. All right, and so that's an important skill. And this skill is identifying that I can use a tablature to get delta H from heats of formation. I can use tablature to get delta S of my system, okay, from this, using essentially the same what? Formulas, and that I can put those values in for delta H of the reaction and delta S of the system. Both are system, right? And using the system's quantities, I can solve for the delta G, which is really what? The delta S of the universe. All right. Now, you can do, and I suggest you do the second side of this, okay, which is very similar to see how you did in review with the key, all right? And I'm going to let you do that. And when you are done, I want you to play me back, and I want to go over the key with you to talk about something particular at the end. All right, so please complete the part, the second side. You can check with the key, but then, play me when you're done. So stop me now. No, stop me now. Okay, so you're done. Good for you. All right, very good. So any case, we're on the back side of the key, and I just want to talk you through this. And now we have methane reacting with 2 oxygens to make CO2 and 2 waters. Now, you guys should have been able to take the tablature data given to you and figure out the delta H of the reaction. Little 0 just means it's standard conditions, and you should be able to get this. And it's also very exothermic, okay? What's different about this is that when you look at the delta S of the reaction, you should have found that, whoa, you got a negative delta S. Now, using the tablature, you get a negative delta S, which means the system's entropy, okay, the system's entropy, the molecular order of the actual molecules are changing in the way that they're becoming less disordered, which means more ordered, which means that you're actually creating, okay, and putting together molecules and creating free energy as opposed to releasing it. So this negative is a bad thing in terms of the universe. But remember, we're measuring just the system in terms of the molecules. So this delta H is good. Energy is being released. We know that the surroundings are increasing, okay, in their molecular motion, because heat is making the surrounding what? Gas molecules around the reaction disperse. But inside this system, we've got a decrease in entropy, which means that the molecules have less degrees of freedom, going against the universe, at least in the system. And that can occur. That can occur. The molecules can be going against. The only way that this process can occur is if we release enough energy to counterbalance that. And I'll talk more about that in the sign reaction. But let's talk about this for a second. You should be able to look at this and possibly look to see why. Now we have CH4 gas, and there are 3 gases. You notice we make a gas, and a liquid. Whoa! Whoa, look at that. We have 3 gases producing a gas and 2 liquids. So 3 molecules become 3 molecules. So it's a wash in terms of individual new molecules, right? And the other side we went from, what was it? It was from 7 molecules to 12. Here it's 3 to 3, so that doesn't change much. But if you notice, if you look at the individual phases, 3 gases become 1 gas and a liquid. As we go left to right, okay, we're becoming more organized. We're putting molecules together. All right, so you should be able to realize that going left to right, you should be able to predict by looking at this reaction that the entropy, not enthalpy, entropy, the delta what? The delta S of my system is negative. All right, and you should be able to do that. It's a very important skill that we can look at a reaction and basically discern what's happening in my reaction. So three molecules becoming 3, that doesn't change our entropy, but 1 gas, or I'm sorry, 3 gases, a 1 in front, right? 1 plus 2, 3 gases becoming 1 gas and a liquid. Boy, just by the phase change alone, we're becoming more ordered. We're putting molecules together. We're concentrating energy. We're going against the dispersion of energy, and that's why my delta S should be what? Negative. If we look at the first side, okay, as a review, we can look at this and say, what? 1 here and 6, 7 molecules becoming 12. That alone increases my entropy, but then having what? A liquid, okay, 6 gases to a gas to make a liquid to make 6 liquids. So this side's really more about the fact that we're going from 7 particles to 12. It's a wash in between how many particles are liquids and gas in terms of the phase changes. So a liquid and a gas to gas. We're not really increasing the amount of gas molecules here, but we're increasing the total number of free particles. 12 are coming out, 7 are going in. Clearly, there are more individual motion particles here, and entropy is positive. We're dispersing energy by molecular degrees of freedom. So very important skill. Can we look at a reaction and evaluate and try to at least come up with a sign? You'll never be able to look at it and know the number. That's amazing. If you can do that, you can make some serious money. But the point is, you should be able to look at a reaction and say, hey, is the delta S of my system, of my molecules' degrees of freedom, positive or negative when you look at it? And here, you should be able to clearly see 3 molecules, and of course, okay, 3 gases going to 1 gas and 2 liquids, okay, is going to make a decrease in entropy. And of course, the math does that. And of course, you should remember to convert your joule mole kelvins to kilojoules, okay? And then of course, plug in your 298 Kelvin, and notice something of delta G is negative 18.12 joules, and the delta H is what? Negative 890. Now, what's different about this problem is we have a what? A negative delta S, which is not a good thing in terms of the what? We are decreasing the universe's entropy in terms of the system. But the reason why this worked out is because we had enough what? We had enough delta H released to overcome this increase in order, or increase in the concentration of energy. All right, and that's something we're going to learn in the next important, okay, lecture coming your way this weekend, possibly. Any case, so if you look very carefully, the free energy is negative 18. Clearly, this process is spontaneous, and of course, the combustion of methane, which is a natural gas, is very spontaneous. A lot of homes in our area use natural gas, and methane is one of them. So it's very spontaneous. There's a pathway. Free energy is being released, okay, or at least it's being available to do work. But notice the heat released, all right, is greater than the delta G available. How is that the heat released is greater than the free energy available? Well, that's because a lot of the what? Some of the energy, okay, the free energy that's released is being used up, okay, to do what? To make molecules become more ordered, or some of the free energy is being used to make free energy and to concentrate energy because of this negative delta S. Pretty cool. All right. Now I have another worksheet that I gave you that's very similar, so if you want to practice, but this is an important skill. You'll see this on your next thermo test.